Hello and welcome to the second session of our Sports Aerodynamics Workshop here at SimScale. Yes, we are very excited to see again so many participants joining our today's session, and therefore let's directly get started. First of all, I would like to make sure that everybody can hear us loud and clearly. So in the case that everything is working fine for you, please click the raise your hand button. Okay, sounds good. Seems like most of you can hear us loud and clearly, and in the case for some reason you should get problems with the audio broadcasting, you can also use our our toll-free audio service numbers to access the audio stream of this webinar. Okay, great. Then let's start to take a look at our today's agenda. Last week we talked about the impact of aerodynamics on ski jumping, and today we will focus on racing bicycles and talk about aerodynamics of racing bicycles and how optimized aerodynamic shapes can help to reduce the drag and improve the performance. First of all, I will just very quickly talk about this workshop, just to make sure, because some people joined the first time this week, everybody knows what we're going to do this and next week. After that, my colleague Akram will give you introduction to bike aerodynamics with some very hands-on and interesting examples. And just after that, we will have a case study like last week discussing the results of a simulation study. And then we will talk about your homework and we will have time for Q&A. Yes, as I mentioned last week, the idea of this workshop series is to put you into the seat of a sports engineer and show you how engineers can help to improve the performance of top athletes using CFD flow simulation to improve their aerodynamics. So every of these, let's say, sessions consists of two parts. First part is a live webinar, where we will talk about fundamentals and where you can also ask your questions. And the second part is a homework assignment which you have to do on your own during 1 week, and where you go to leverage the SimScale platform yourself for optimize or investigate the performance of the sport device. And just because some questions are asked again and again, yes, we will record all this workshop sessions so you can access them later. We will send you also a link to the recording. You will get support also for the simulation on our forum. I will show you later where to find this forum. And if you want to learn something about topics which are not covered in this session, you should also access our large library of free learning resources, which you will find on simscale.com. Yes, and now I'm very happy to give the word over to my friend and colleague Akram, who will do the introduction about bike aerodynamics. Have fun.
Hello everybody, can you hear me?
Yeah, we can hear you.
Okay, great. So good morning, good afternoon, good evening, wherever you are around the world. We really appreciate your time for joining us for this second session of our workshop, Sport Aerodynamics. So first of all, quick overview about me. My name is Mohammed Akram Mufak. I'm a user success engineer at SimScale with aeronautical engineering academic background and extensive experience in working in the field of CFD and applications of aerodynamics. So as Milad already mentioned, so first of all, we're going to have an introduction about aerodynamics of bikes, and then we will have a case study where we will discover more things about the aerodynamics of this application. So to start, I have this great video, like motivation for you to show you the effect of aerodynamics on bikes and what aerodynamics can do. So let's play this video and I'm going to comment on it to see the effect of aerodynamics. So here we can see this rider who is riding his bike and everybody can overtake him. Like we can see that he's really slow compared to the others and he's trying to reach them. But for the moment we can see that they went far away from him, but now he activated the aerodynamic effect. And look at his position. He changed his position from the cycling movement to an aerodynamic Superman shape. And we can see that even without cycling, he can overtake them with twice the velocity of the other bikes. And not only this, but look at the next step. He's overtaken more bike with high velocity without cycling without moving his legs. Why? Because of the aerodynamics and because of the acceleration of the gravity. He went far faster than anybody in the circuit. So now let's talk about more about the aerodynamic of bike. So why bike's aerodynamics is that complicated and why all this complexity? So first of all, due to the shape of the rider. And because we know that the rider is a human being and the body of the humans, it's not designed for aerodynamic movement. So that's why aerodynamics of bike is really complex, not only because of the static shape of the rider, but also because of the cycling movement. This will create a high complexity for the flow, and the flow is totally transient, and the behaviors of the flow is really complex. So that's why aerodynamics of bike is really complex. The interaction between the rider and the bike, it's really important. What I mean by this is the position of the legs, the position of the arms, how the back of the rider is positioned. All these things, so the interaction between the rider and the bike, it's a really important factor to ensure the performance of the bike. Not only this, because for bicycle or for cycling aerodynamics, usually you will not cycle alone in the street, but always there is a couple of riders riding with you. So the position of the rider, depending from the front to the back, or if you have another rider behind you, this will completely change the aerodynamics parameters and the aerodynamics performance. So as you can see, aerodynamics of bikes, it's not a fixed science, but it's influenced by a lot of parameters. And to understand a little bit the effect of aerodynamics of bikes on the performance and what we can gain using having like high performance aerodynamics for our cyclists. So let's assume, for example, we reduce the drag of the cyclist by 2 newtons, and imagine for the previous video, I believe that this rider here reduced his drag by 60% or more, because totally like if we will decompose the aerodynamic forces of a cyclist, we will say that it's between 80 to 90% of the total drag of the bicycle or the cyclist is by the body of the human or the athlete, and all the rest is for the bike. So here we can assume that we have reduced our drag by 2 newtons for a velocity of 13 meters per second, and let's assume for maybe 250 kilometers of distance, which is like typical length for a cycling stage. And if we do some maths, we can see that we have reduced or we have gained 65,000 kilojoule, and if we convert this to calories, we can see the number. And if we do some relation between these calories and what the rider have to eat to get these calories, it's around 3 plates of chocolate. So as you can see, for just 2 newtons, how many energy or how many power you can save for your rider. So it's really important to have the right aerodynamic performance, aerodynamic shape for the bike. So now let's talk a little bit about some physics, and let's discover the forces acting on the bike. So if we consider that this y over here, or the v velocity, it's the speed direction of the wind, so here we can see that we have, first of all, the propulsion of the rider, which is created by the cycling movement, and also with the blue arrow we have the drag force, which is in the opposite direction of the propulsion and the movement direction, and we have the gravity force, and also we have the reaction of the ground on the tires. This is in straight riding condition, but let's take an idea about sidewind riding, because usually when you ride the bike at 10% of your cycling, let's assume, for example, you are cycling for 200 kilometers, just 10% of your cycling cycle will be cycled in 0 yaw degree or 0 sidewind force. So to make sure that you have the right performance, you have to consider your optimization or your study in different your angles. And this is exactly what we did in our case. So we will show you exactly later the effect of the side wind. And here, if we can take an example, this example, so here we have the rider with an angle created between the moving direction and also the velocity of the wind. And we can see here that the DD, which is the real drag that is acting on the rider, and here we have this SD, which is the, or SB, which is the side force acting on the rider. But actually, if we will do some calculation on the wind tunnel or CFD, usually we get the DW and the SW. And that's why it's really important to do some math to get the right direction of the forces acting on the rider, to get the right the representation of the side force and the drag force. And here we can see that, for example, if you want to calculate the right drag force acting on the rider, you have to calculate this force over here, the DW, which is the drag on the flow direction, and cos theta, which is this angle between the rider or the bike and the wind direction, minus SW, which is this component over here of the side wind, multiplied by sinus y, which is the angle between right and the accurate values of forces acting on the bike or the rider. And here we can see, for this example, we have two similar simulations for two bikes with the same conditions. The only difference here is the wind direction. So for the first one on top, we have the wind direction with 8 degrees, so the wind is coming directly facing the rider. And for the second one, we have a side wind with 20 degrees, and we can see clearly that the effect is significant, and we can see that the pressure distribution over the rider and the bike is completely different, and this will create different forces acting on the rider and the bike, and that's why it's really important to investigate the side wind. And like I said, just 10% of the total riding cycle is considered as straight riding. Always there is the side wind. And here we take the same example like the previous one, but here we are visualizing the pressure coefficient from the front. And we can see clearly how the pressure coefficient is shifted a little bit to the side because of the side wind. And this will have an effect on the drag created by the bike and the rider. And another example that we can see here, it's the total pressure or the kinetic energy in the flow. And here we can see the wick structure of the two bikes, the same bike, the same rider position, but just with a side wind. And we can see that the flow structure is completely different. And what we are looking at now, it's the energy in the flow. What this means, when we have this red region there, the flow velocity is really high, so the kinetic energy is really high. And where we have the red, the green, and the yellow color, so over there, and also a little bit blue, so there the velocity of the air is really low. And it's really interesting for a rider, if he's following another rider, to be inside this low kinetic energy region, because this will reduce the drag of the rider following the other one. And we will see this in more details in next slide.
Akram,
so here it's
sorry for interrupting you, but there is just a short question by Thomas who wants to know what the pressure coefficient describes. So maybe you can answer this question in between.
Yeah, what is the question again?
What the pressure coefficient describes.
Oh, okay. So instead of using the pressure like the pressure as physical quantity, usually when we compare different designs, we usually use dimensionless values, and the pressure coefficient is the dimensionless value of the pressure. So usually it's in between 1 and -1. So this will give you like a stable range range to evaluate your different designs with the same range, because usually if you use the pressure and when you change the design, sometimes it's a little bit difficult to get the same range, and this will give you better understand of the performance of your design. I hope this is what he's looking for. So here we can see for this slide here the same physical quantity as the previous one, which is the total pressure. And as I said, the total pressure is the static pressure plus the dynamic pressure, and the dynamic pressure it's half rho v squared, and it's the same formula as the kinetic energy. That's why we have already mentioned that total pressure is the kinetic energy in the flow. And here we are looking to the slice, moving from the bottom to the of the bike, from the ground, moving to the up to the helmet of the rider. And we can see from the left side we have the yaw angle equal to 0. This means we don't have side wind, and from the right side we have 20 degrees. With 20 degrees we can see clearly the size and the shape of the wake is significant compared to the no yaw angle. And as I previously mentioned, so here we can see here in this region over here, so in this region, the flow, the kinetic energy in the flow is really low. So if a rider is following this rider in this region, he will use less energy to get the same velocity as if he's riding over here in this region of the red or high kinetic energy. And to confirm this, so here we have two different riding conditions. So the one from the left is called the front wind riding drafting condition. Or because of the surrounding buildings and so on, there is no side winds, so it's important to ride in this condition just behind the rider in front of you, because you will take advantage from this bubble that is created behind the rider in front of you of low kinetic energy. So you will not use so much energy to create the same propulsion as if you are just here in the free stream. But from the right side we can see that the riding position, it's not the same, but they are riding in like in a drafting position, but from the side with an angle. And if we can see, there's two rows, and the idea is because the air is coming from this side, it's with yaw angle equal to x degrees. And if we can go back with one slide, we can see that they are riding just over here. So for the slide with the riders riding beside each other, so they are riding just in this region, and for the other one where they are riding just behind each other, they are riding here in this region. So this is really important to take in consideration when you are riding, because we have already talked about the power that you can gain if you can reduce this drag, and actually this will reduce a lot of drag and can help you to get more endurance to ride for a long distance. And as we have already mentioned, two newtons of drag reduction can give you a gain of 3 plates of chocolate. Okay, so here we can see in this 3D structure of the flow how the side wind can completely change the flow pattern of a rider with a bike. And here we can see, first of all, from the left side we have the yaw angle with 0 degrees, and from the right side we have yaw angle with 20 degrees. And actually the flow is completely different, and the most important thing that I want to mention here is the flow over the tire, where we can see here that the flow is almost attached to the tire, but from this side the flow is completely detached, and the separation is remarkable over here. And also you can see these forces that created just here because of the difference of pressure between this side where we have the stagnation pressure, and this side where we have the wake of the low static pressure region. So just for credit for the previous pictures of the video and the front wind riding and side wind riding. And now let's jump to the case study, and I'm glad that Milad will join me for this part of the presentation. Milad?
Yes, I'm back. Akram, do you have just a question in the
Okay, perfect.
meantime by Mislav? You may remember
Okay.
him. He made this great blog post on LinkedIn about the Formula Student Workshop.
Oh yeah, that's right. Hi.
And he is a little bit confused, I think, because we talked about dirty air during the Formula Student Workshop, and he just asked if it's not better to drive like on the second picture. And I think his question is more or less if these vortices are not like a disadvantage for the following driver, like in motorsports, for example.
Yeah, also for motorsports, it's really important to drive behind like another rider, because this vortices actually will, well, maybe. So we will not talk now about motorsport, because in motorsport, if you are riding, for example, for Formula 1, if you are riding behind another one, this will reduce your downforce, but also will reduce your drag, so this will help you to overtake him. But here it's completely another case. Here we don't have the downforce, we don't have lift, so we are not interested about the effect of the front rider on you in terms of lift or downforce, but only for drag, and drag will decrease dramatically. And I can tell you from my experience, I know that this can reduce from 30% even to more if you are riding behind another cyclist.
Yes, I think really
Because
the main difference is the application. As we discussed last
exactly.
week, Formula 1 or motorsports is one of the few applications in sports where you need downforce or lift. And in motorsports,
Exactly.
it's the same. It's on the straight for overtaking. The dirty air is helping you. The problem is that you have to corner also, and in the corner you need the downforce. But I think we are leaving a little bit the main focus for our discussion. Mislav, I hope this answered your question. We have some more questions. Let's try to answer them all together at the end and continue with our case study right now.
Okay, perfect. So as I already mentioned, Milad will join me for this section of the presentation. So let's talk about our case study. So for our case study, we have decided to work on the front, or let's say both wheels of the bike. But why exactly we have decided to work on the wheels of the bike, or the tires of the bike? So first of all, because the wheel drag is responsible for 10% even to 15% of the total aerodynamic drag of the bike. So that's why it's really important to investigate this part. One other important thing is finding the right wheel design can reduce the drag by as much as 25%. What I mean by this, for example, if you start with an initial design, and then you can do some optimization on your wheel design, you can gain 25% from the original design just because of the right profile of the wheel. Another important thing is overall reduction in the drag can be on order to 2% up to 3%. What I mean by this, the performance of the tire can reduce the total drag of the rider with the bike by 2 to 3%. And if you remember our example of the calories that the rider need to ride over 200 kilometer, this can have an important effect on the performance of the rider. The last thing is tires are the most important thing, or important part for bike or road bikes or racing bikes. So it's really important to have the right set of tires with your bike. Maybe Milad have another comment on this.
I think also a reason is, I mean, we will show you just in the next seconds how we use simulation to optimize, let's say, this area of the bike. And if you think about designing a bike, it is quite hard to modify the chassis or the frame after you have designed and manufactured it, especially since most of racing bikes are made from carbon fiber today, which means that it's very hard to change the tools. In contrast to that, the wheels can be changed quickly, so this is, let's say, a quick win. And if you're going to optimize a bike, that's the first thing you should do. And I think what people are really interested about Akram is how we leverage the SimScale platform to investigate this. So basically what we did is we investigated, maybe you can show the next slide, Akram. We investigated 3 different wheel designs in terms of the yaw angle optimization. So we changed the yaw angle and just investigated how, let's say, sensitive different design reacts of the change of the flow conditions. And we have a thin wheel solution, a mid wheel solution, a large wheel solution. As you can see, it's a real big difference. So the large wheel is not anymore looking for me like a bike wheel, honestly speaking, while the mid wheel, I would say, is how my bike's wheels are looking like. And yeah, let's see what the effect is, Akram, right?
Okay, perfect. So just like Milad already mentioned, so we will do this case example where we have 3 different designs, and just to let you know, the cross-section of the tires is the same. The only difference is in this parameter, the chord length, because actually the profile of this wheel, it's almost as a wing because of the curvature and so on. So all what we did is the parameter of chord. What I mean by chord is the distance from here to over this distance over here. And maybe Milad, he mentioned that this tire over here, it's like not, that's right, we will not see this kind of bikes in the streets, but actually this bike tires, it's really applicable and it's really used in the closed circuit bike racing. There is like famous racing series inside a ring and closed ring, and we will talk about the reason why they use this kind of tires in the next few slides. So here, beside this case example of the parameter, the geometry parameters that change the chord length of the tire, we have another parameter which is the yaw angle. And for this yaw angle, we will do 3 different yaw angles, because based on some statistic results, we know that for the majority of the cycling cycle, the riders are riding in between 0 degrees, or let's say 5 degrees, to 20 to 25 degrees, depending on which kind of riding you are, or which kind of circuit you are riding on, if it's mountain or just highway or in the city. So it's dependent on these parameters, but the rider spend the majority of his riding or cycling cycle in between 5 degrees to 20 to 25 degrees. So here we have the 15 degrees, and also we have the 20 degrees. So we have 6 parameters for this simulation, or for this case study. 3 geometrical parameters and 3 physical parameters. So now I want to give you just an overview about CFD and how we do simulation of a bike and how SimScale works, or any CFD software, the process of CFD. So first of all, we need the CAD model, and this CAD model has to be like watertight with some characteristics that is there is no gap on the surface, there is no open edges and so on, and with a discretized domain. So as you can see here, we see this bike and also we see this domain, because we can't resolve our governing equation all over an open domain, so we have to discretize our domain to get like representation of our physical quantities. So after doing this, we need to create a mesh. And what is a mesh? Is discretizing this large domain into small control volumes that we call it cells. And these cells have like shape, and as you can see here, and the density of these cells are controlled by the region of interest. So for example, we have high density over here because there is weak structure, so there is high gradient in the physical quantities. So that's why we use high density instead of this region where there is no effect. So that's why we have large size of the cells over there. And here in this picture you can see just the mesh of the surface, but actually in reality there is boxes that cover the whole geometry of the rider. The next step will be to apply this equations, this mathematical equation that describe the movement of the flow of the fluid over space. And here we have what we call the Navier-Stokes equations, which is the continuity equation, the momentum equation, and also the energy equation. But for this case, we are not using the energy equation because we don't have any compression condition and thermal effect. So we are using only the first two equations, and what we are doing, we are applying for every and each and every cell from these ones these equations. So then what we will have, if we will resolve these equations in this space, we will have a cloud of values that describe our flow motion over our cyclist. And this is what we can see here. As you can see, there is these small dots. These small dots are at the center of every cell. And the density is changing because I told you of the size of the cells. We change this size according to the region of interest. And later, the next step, using some numerical approaches. So what we will do, we will interpolate the values between the two or three points to get this smooth distribution of the physical values. And this is the process of CFD and how we can use the computer to resolve this governing equations, and then we arrive to these pictures that should give us better explanation about the flow moving over an object. So now let's jump to the results. And as we have already mentioned, we have three simulations or three geometries with three condition of riding. So with 0 yaw angle, with 15 and with 20. And let's start with the 0 yaw angle with different geometries. So here we can see from the top right side the rider with the bike, and this plane over here cut the bike over here, and this is what we are looking at in this picture from the left side. It's the total pressure. We have already talked about what is the total pressure. It's the kinetic energy in the flow. This means if we have red high value, which is 1, there is no disturbance in the flow. The flow is clean with high velocity. The red and the green and the orange or the yellow color over here, it's the low energy in the flow. With the 0 yaw angle, we can see clearly that here, this point here is the front tire, and this is the X of the front tire. Here are the feet of the rider, and I think you can imagine it if you can just look at the picture over here. So this point here, it's this point over here, because we are cutting the flow in this point. And what we can see over here, we can see that the flow over the front tire, we can see that we have strong wick behind the front tire, the thin tire, and this is really important. That's why usually for cycling or for athletes that cycle, they never use these thin tires. Why? Because there is a large separation behind tires, and the wick structure is really strong, and this will create a lot of drag force because of the difference of pressure between the front and the back of the tire, and we will see this better later in the next few slides. If I'm gonna jump to the next slide, we can see that there is something changed, and it's the size of the tire. Now we are talking about the mid-size tire or the mid-thickness thick tire, and we can see, if I'm gonna jump back, and you can see here that we have strong separation over here, and for this one the separation is reduced a bit. That's right, it's not really significant, but it's reduced. So we can say that the size of the tire or the size of the thickness can dramatically impact the performance of the tire in terms of drag. Let's jump to the next one, and here it's remarkable, and it's clear that with the large tires the wick is really small, and I'm gonna tell you why. The idea is, for the thin tire, the flow moving beside the tire just over here, will not have enough space to develop the boundary layer. So it's still laminar boundary layer, and that's why this flow cannot stay attached over this curvature in the back of the tire. But for the large tires, the flow have more space to develop the flow, and that's why we have this transition from the boundary layer from the laminar one to the turbulent one. And we know that the turbulent one, the shear stress is higher, so that's why the flow can stay attached over this side surface and a bit over the back of the tire. And sometimes there is also a lot of companies that they use rough surface over this side, over the side of the tire, to make sure that you have turbulent boundary layer, to make sure that it's still attached over the tire. Maybe Milad have another comment on this first slide.
Yeah, I think one point is very important, which you mentioned, the turbulence boundary layer or turbulent boundary layer. And a lot of people get confused. So turbulent boundary layer, laminar boundary layer, it's not the same like turbulent or laminar flow. Here we're just talking about the flow in the near of the surface. And if you want to get an idea between laminar and turbulent boundary layer, just imagine a laminar boundary layer is made of parallel layers of air moving, while in a turbulent boundary layer you have some mixture inside, an increased impulse exchange in y-axis. And that's the reason why a turbulent boundary layer is much more stable and will also later later deattach.
Yeah, exactly. And just to give you like the formula that why we need like turbulent boundary layer. So we have tau, which is the shear stress, is equal to mu, the dynamic viscosity, multiplied by the gradient of velocity. So if we want to increase our tangential effort on the surface, we need to increase either the dynamic viscosity, which is not possible, only if you will change maybe the temperature of the fluid, or you change the gradient of velocity over the y direction or the perpendicular direction to the surface. And to do this, you need to change the profile of the flow, and to change the profile of the flow you have to create turbulent boundary layer, and this will increase the tau, which is the wall shear stress, and this will make sure that your flow have more tangential effort to stay attached over the surface for a long distance. So let's jump to the second parameter, which is the 15 degrees, and here we can see our bike at 15 degrees, and we can see clearly the effect of the side wind on the flow over the bike. And we can see here for this small, the thin tire, that the flow is highly detached, and there is a strong separation over here, and the recirculation as well, and also for the rear tire, or also for the rear side of the front tire. But if we will jump to the next one, we can see that there is separation, but if we take a close look, so here the separation is started a bit earlier compared to this one. So this one, the separation is not really earlier like the previous one. And for the large tires, we can see clearly that the flow is still attached even a bit on the curvature of the tire. Where maybe it's not really clear here, but if we zoom in a little bit, we can see that the flow is still stay attached over the tire, or even behind the tire, where for the previous design were like completely detached. And this is really important because of the turbulent boundary layer that is developed over the side of the tire.
But I think, Akram, we have a leading edge separation on the other side of the wheel, right? If you take a look.
That's right. That's right. We can see here clearly that we have separation from this side, but actually later when we will see the results, we will see that this design of the large tires will decrease the drag dramatically, but will increase the side force because of the large area. We will see this later in the next slides. So at 20 degrees, we can see at 20 degrees there is no way to the flow to stay attached over the tires, and it's completely detached, and the separation is remarkable for the three different designs. And we can see here for high side wind, the flow is totally separated over the large tire or even the mid-sized tire. Maybe Bilal, you have a comment over this one.
Not really. I think you talked about most of the important things. What I really like about all this picture, it really shows the trade-off you have. For example, if you have the large wheels, on the one hand it's stabilizing the flow as long as you have no yaw angle. But from that moment on where you have yaw, it can also be a big disadvantage, like the large wheel which is acting in the end like a plate in the flow. And I think this really shows that there is not the perfect wheel for any conditions, but that you can use the dedicated specified design for every application. For example, for hill climbing, you would use another kind of wheel, like for driving on a highway on a street race.
Exactly, I totally agree. Like any application, when you talk about performance, performance is related to the operation condition. So, like I told you before, and we will show this when we talk about the graphs and the forces. Actually, this tire, it's really, really efficient when you don't have a side wind. So, for this competition where you have like closed circuit, where you don't have a side wind, this tire can make the difference in terms of performance, because the drag of these tires is really low compared to the others, but the side wind is really significant. Okay, so let's jump to the next. So here we will see a lot of interesting things over this slide. So for this slide, we are talking about straight riding, no side wind equal to 0. But this time we are not creating slice over the vertical direction, but over the lateral direction of the rider. And exactly, we are cutting the rider in the middle, and we are visualizing the same physical quantity, which is the total pressure. And here we can see for the first picture, here we have the thin wheel, and we can see that we have a large separation over here, and the wick is significant. Also for the wick that is going to the back of the tire, I mean the back of the bike is quite significant, and the separation here, it's remarkable, and this will reduce, or this will increase the drag of your bike and will reduce the performance of the rider because of the drag created by this tire due to the separation that I have already talked about. Because as you can see, this distance is quite small or short, so the flow will not have enough distance to develop to a turbulent flow. So that's why we have separation over here.
And I think the effect you can also see is related to the rotation of the wheels, because a lot of people are asking. And first of all, yes, we considered rotation of the wheel, so therefore we used a special boundary condition, which is applying a rotational velocity on the surface of the wheel. And that's the reason, for example, why you have this flow structures inside the wheel, because you have a higher flow velocity outside than inside the wheel, and this will produce vortices, which are then creating this disturbance. And in this image you can really see, I think, this effect of the rotational wheel due to the flow separation and pressure fluctuation effects inside the wheels.
Yeah, exactly. If we are using like static wheels, this will create completely different results, and the results will not be accurate. But let's focus now on our slide, and let's jump to the next design, which is the mid-size. And we can see even for the mid-size, of course, we have reduced this this separation a bit. The wick is not as strong as the previous one. I can move back. So as you can see here, the wick here is really strong. This wick that is going directly to the back of the bike, and also here, as you can see here, with the mid-size tire, we have reduced this wick significantly. But now it's the surprising result. It's when we use the large tires. The large tires create like really smooth flow behind it, and it's really important to reduce the drag of the tires. I can show you again, if you can focus here on the tire, here for the mid design, we can see that the flow is really turbulent. There is significant separation over here. Also the wick created behind the tire is really remarkable. But if we will jump to this one, the large tire, we can see that the flow is smooth, and there is not as much flow separation as the previous designs, and it's really important to ensure the performance of the cyclist. Maybe Bilal, you have another comment on this one.
Not really. I think I would just tell you what I told again, and I think here you can really see the effect of this long wheels which is stabilizing the whole flow around the wheels, and that's the reason I think why this flow is looking so much smoother and stable compared to the other two wheel designs.
Exactly. So here we will show now the effect of the side wind on the pressure, and from the left side we can see the side where the flow is hitting the bike, or like there is a component of the flow velocity from this side, and this side from the right side hand side, it's the wick region, and we can see that for the thin tire we can't see like really significant effect on the difference of pressure. I'm talking here about tires. I'm not talking about the whole rider and bike geometry, but just on tires. And that's why these tires, the thin tires, are more, the performance can be better for side wind, because you will not have as much side force as the large bikes or the large tire, but actually they create so much drag compared to the other large tires, and we will see this in the numerical values. Here we can see the mid-size tire, and here we start to see the effect of the difference of pressure between the stagnation region and the wick region. So here it's from where the air is hitting the bike, and we can see that we have high pressure from this side but low pressure from the other side. But for the large tire it's totally remarkable, and we can see this clearly, that we have high difference of pressure between the impact side and the wick side, and this will create really high side wind, side force, because of the difference of pressure between the two sides. And here is the graph that I want to talk about. So here we have TW, it's the thin wheel, MW, it's the mid wheel, and LW, it's the large wheel. And here we are visualizing the angle of attack with the bike forces. So for this graph here we are talking about the forces. We are not talking about the total force over the bike, not the tire separately. And from this side we can see the side forces on the bike, acting on the bike with different angles, and we can see that the large tire, as we have already talked about, creates so much and affect the performance of the bike in terms of side wind significantly. And we can see that there is high side force acting on the bike when we use the large tires, and for the thin tires the side force, it's really low. But actually the side force is not really important, because we are more interested about reducing the drag than reducing the side force. And if we are looking for the side force or the drag force, we can see that the large wheels create less drag than the thin wheels, and this is the surprising results, that large tires create less drag than the thin tires. And as I mentioned, the lateral or the side forces is not really important, because we try to reduce the drag of the bicycle to make sure that our rider will not face a lot of resistance when he is riding, but the side force is not important. So that's why when we increase the size of the tires, we are increasing the side forces, that's right, but in the same time we are reducing the drag of the bike. Milad, maybe you have a comment on this one?
Not really in this case. Maybe let's proceed with the next two graphs we have.
Okay, perfect. So here in this graph, now we are talking only about the tire, and we are talking mainly about the front tire. So the same names, TW, MW, and LW, and what we can see from this side, it's the drag force. And we can see that the drag force of the large tire is the lowest one. And this is really surprising results, because for the tire, for this thin wheel, we can see that the drag is quite high. It's like we are reducing, if we are riding at 20 degrees, we have almost reduced it's more than half drag. We can reduce it just by changing the size, I mean the thickness of the tire. It's from I think 1 Newton to 0.3 Newton, which is really significant. But as we can see from the lateral force or the side force, of course the large tire creates significant side force because of the difference of pressure between the two sides, and also the geometry and the area of the tire. So,
and that's, I think, Akram, very important to understand, as I would say a very familiar misconception in aerodynamics, that drag is not because of the friction between the air and the surface, or not mainly, but because of the pressure difference before and behind the object. And this, I think, really shows that. The large wheel has a higher, let's say, surface, a larger surface. You would expect it to have more drag, but since the flow is not separating so much and is just, let's say, much smarter going around the wheel, in the end we have less drag.
Exactly, and because in aerodynamics we have two concepts, like you have mentioned right now. We have some geometries that create more pressure drag, and some other geometries create more skin friction drag. And I'm gonna give you an example over here. So for bikes, if we are taking consideration the rider, it's 97 or 95 to 97% of the drag created by the rider. It's pressure drag because of the difference of pressure between the stagnation pressure in front of him and the weak low pressure behind him. So it's almost totally pressure drag. But if we are talking about tires because of the aerodynamic shape, so the drag is more created by friction than pressure drag. Okay, so here we can see, as we have already commented on this graph, so it's remarkable that the large tires give you more performance in terms of efficiency, in terms of reducing drag, but will give you more side force. Okay, so here we have this conclusion. So what we have, so from the left side we have thin tire, in the middle we have the medium wheel, and in the right side we have large wheel. So the idea is, if you are using thin wheel, expect that you will have high drag with low side force. But for a medium-sized wheel, you will expect to have like a balance. You have the balance between the drag and the side force. So you will not have so much drag or so much side force, but it's balanced. But for large wheels, you expect to have low drag but high side force. So it's really important to remember this when you are an athlete riding, or you are a designer trying to find a better design for your wheels. So some design suggestions. So the wheel thickness can have significant effect on the whole performance of the bike, and as we have already figured this in the previous graph, is that the tire, even just by changing only the tire, you will see significant changements in the performance of the whole bike performance. The drag decrease with the large wheel, but the side force increase, and we have already talked about this in the previous slides. When we decrease the drag force, by increasing the chord of the tire, we will increase the side force. For riding without side wind or a closed circuit, as I have already mentioned, we suggest to use the large wheels. For riding with significant side wind, we suggest to use the medium to thin wheels, depending on what you're looking for. Okay, so that's all what we have for today. I hope this presentation was helpful for you to discover new things about aerodynamics of bikes and how you can use SimScale to do this. I think now we have, I think Milad will talk a bit about the homework and the work that you have to do, and then we're gonna jump to the Q&A session. Milad?
Yes, I'm here. I think we can just continue. You can stay the presenter. Maybe you can go to the next slide. Okay, guys, so you just got a very interesting presentation by Akram and some insights into the world of bike aerodynamics. And as you know, this course is not only about listening, but also about doing yourself something. So you will have a homework for this week, which is about investigating a bicycle wheel under the two different side slip angles. So we will provide you with a project including the geometry of the wheel, and your job is to investigate the influence of the side slip angle with help of a simulation. Everything you need, you will find it on simscale.com /sports, where you will also find the step-by-step instructions and where you can submit this homework. And by submitting all three homeworks, you can qualify for a certification of participation. And if you need help, just check out our SimScale user forum, where you will immediately get help. Yes. Okay, and if there are no questions related to the homework, I think we should talk about two remaining questions during the session. First of all, them is by Maury, and he wants to know if inclination and declination of road would affect pressure coefficient or the pressure distribution around the bike in general.
You mean like you're riding over a slope?
Yes, or if you're riding down a hill or climbing up a...
Yeah, of course. Of course, this will completely change the stagnation point, and this, if you change the stagnation point, this will change. It's dependent on the. Yeah, this will affect for sure if you are riding in different angles, but I don't think if the impact will be really significant, because if we just change this angle, we will, because there is the ground, and I don't think if there is a rider who can like ride at more than 20 degrees. So for the normal riding conditions, I don't think if you will see effects.
Right, thank you very much, Akram. And the next question is by Thomas. I think it's a more general question, and he wants to know if there were other, or let's say if the current posture of the biker are really the best, or if there are not maybe other concepts where you know this bikes where you lie on, for example, which would be better.
Yeah, of course. Actually, there is three different positions of the rider. And when I'm talking about the position, I'm talking about like the large positions. Like there is three. Like there is TT, which is time trial, where they have this position where they lie in front and they hold like the steering bar like really in front. So this position, it's mainly for TT or time trial. So they try to find the position to like reduce the drag as maximum as possible, but this position, you can't ride with this position for 50 kilometers because it's in comfortable position. It's just for going so fast as possible, but you can't hold this position for a long time because it's not comfortable. There is the second position, which is the one that I'm showing over here in our presentation. Maybe if you just can find it. So over here, this position is like for when you try to go fast, but also with a comfortable position. So usually they use this position when they want to overtake because the drag here it's really low. And the third position is the stand-up position where they don't hold over this curve over here, but they hold over here and they stand like there is more area facing the chest of the rider is facing more air, and this position is comfortable but not the aerodynamic shape. But this position, it's the perfect position for like long distance riding with a low drag.
All right, and there's a final question by Kamran, and he wants to know, how does the drag difference justify the weight of the bike? Is it good to go for more thicker tires as an engineering design? And I think, Kamran, this is really a general question. So in the end, you can calculate it. You can calculate, like, for example, the trade-off between, let's say, increased weight of the wheel of the bike compared to reduced drag. But yes, maybe Akram wants to add something on this.
Can you repeat the question, please?
He wants to know how does the drag difference justify the weight of the bike. So, for example, if you use a larger wheel, the wheel will probably have a higher mass, and then it's like a trade-off. And
yeah,
what is the better approach?
Actually, yeah, that's right. But the weight of the bike is not important for this condition. Maybe I'm gonna like tell you something. If you take the TT bikes, which is like the time trial bike, where they have this really high fancy geometries, where they have this fancy helmet with the smooth shape, and so for this bike, the weight of this bike is 3 times the bike this one. So because of the large size of the frame, so that's why the weight is really high. And actually, I don't think that the weight can affect the performance of the bike. Of course, this will have an effect, but for aerodynamics, not really. And this parameter of the wheel size maybe will increase by a few grams if you are using carbon fiber as material. So I don't think if this have an effect on the performance of the riding. And as I said, the high performance bikes, and I mean the high performance aerodynamic bikes are they weight more than the normal bikes.
Yeah, and you should not forget that weight has only impact while you're accelerating. When you're driving at a constant speed, in theory, the weight has no effect. Okay, guys, there is really the final question by Fabio. And he wants to know, the medium-sized wheel is one graph showed completely opposite behavior than the thin and the large. Is there a reason?
Yeah, that's right. I see. Actually, I've checked like closely the results, and I've seen that there is a different just here. If we can look, that it's like the wheel and the tire, there is like a small gap, and this gap like really creates like separation over there, and I guess this is the reason. Yeah, I think this is the reason why.
All right, okay, then great. If there are no questions anymore, I think we are done for today. There's a question by Michael. Does the car moving after the cyclist will reduce the drag? I think that's it. No, after the cyclist.
Yeah. Actually, this is a really interesting topic that maybe we can like close our discussion about it. Maybe if I will go a bit, to the top, because this is really interesting question, and yeah, this will affect. Maybe if I'm gonna talk about here. So what's happened if a car is riding after the bike? It's from here, from the back. So what's happened is that the car has a stagnation pressure in front of it, okay? And what's happened if the car is just here, so there is high pressure behind the rider. And this what we'll do, will decrease the difference of pressure between the front of the rider and the back of the rider. You know what I mean?
Yeah, I think it's clear. It's like blocking the domain from behind.
Exactly. So it's like you have more pressure pushing you from the back, but it's not the right definition. But the car from behind you will reduce the low pressure behind you by the stagnation pressure that the car creates.
Yes, but I think this is something different we would have to investigate. If someone of you is interested,
Exactly.
feel invited to simulate it on SimScale and share the results with us. Guys, thank you very much for being with us today. Akram, thank you very much for your time. It was really a great demonstration. I hope to see you next week.
Many thanks for you. Yeah, many thanks for you and for all the participants. We really appreciate your time and looking forward to see you in the next session.
Yes, next week, Monday, same time, same place. Guys, have a nice week. See you soon. Bye.
Bye-bye.